Section 2.4 starts on page 130, but the chain rule is on page 131. And it's a pretty good read here. It says, if y equals f of u, f of u, is a differentiable function of u, and u equals g of x is a differentiable function of x, then y equals f of g of x, right? F of u, but u equals g of x, so it's f of g of x. It's a composite function, is a differentiable function because u and g were both differentiable functions. And here's how you find its derivative. The derivative of y with respect to x. That's the way you need to think of that. The derivative of y with respect to x equals, and then dy du means the derivative of y with respect to u, so that'd be the derivative of that, times du dx. That means the derivative of u with respect to x. That'd be the derivative of that. So it ends up being a product. The derivative of this composite function ends up being the derivative of the function that has a variable of u times the derivative of the function that has a variable of x. Okay, just hang on to that for a minute. And if you can follow that, you're more man than I. And some of you are definitely more woman than I. So regardless of whether you can follow that. All right, so for composite functions, the derivative of y with respect to x, which is what we want the derivative to have x as its variable when we're done with it, equals the derivative of y with respect to u times the derivative of u with respect to x. And then I wrote it out there the same way the book does. Now, this will start to make a little sense to you when I work an example for you. So, here's our example. Write this down. We're going to find dy dx, the derivative of y with respect to x, and this is y. Y equals x cubed plus 1, that quantity, to the 7th. And you can see here, we do want a way to find this derivative without multiplying that out, don't we? I mean, that's going to get very difficult. It's going to be difficult if we tried to use the definition of derivative, the limit, delta x approaches 0, that'd be really difficult. It'd be difficult to multiply that binomial times itself 7 times. Once we did that, then taking the derivative would be easy. But doing that without messing up a sign or a number somewhere would be extremely difficult. So we need a better way. Well, here's the better way. The chain rule says that the derivative of y with respect to x equals the derivative of y with respect to u times the derivative of u with respect to x. U. We need a u. Well, the u is the quantity. So u is x cubed plus 1. So we can think of y then as being u to the 7th. So you see how it's starting to use some of the notation that I have up there highlighted in yellow. We have u's and x's and y's. Okay? So according to the chain rule, then the derivative of y with respect to x, or let me just say it in symbols. Dy dx equals dy du times du dx. So we need to figure out what dy du is. So that's the derivative of y with respect to u. Look, right there. If I said take the derivative of that, it's 7u to the 6th. It's just the power rule, isn't it? So the derivative of y with respect to u, with u being the variable, is simply 7u to the 6th. Times du dx. That's the derivative of u with respect to x. Well, look, here's u over here. So if I say take the derivative of that. What's the derivative of x cubed plus 1? It's 3x squared. The only problem we have now is that we have a u and an x in our derivative, but what are we trying to do? Look, it's called dy dx. We're trying to get it all written with x as the variable. So what do we do now? How do we get rid of the u? Yes, substitute back in. Substitute the x cubed plus 1 in for the u. Now also multiply the 3 times the 7. Okay? So I multiplied the 3 times the 7, and then I substituted the x cubed plus 1 in for the u. And I guess I should have written in a special step. 7 times x cubed plus 1 to the 6th times 3x squared, and then I simplified it. That make it a little more clear. I should have made the first example as clear as I could have, shouldn't I? So that's my answer. And then it is everything a derivative is. It's a formula for the slope of the tangent line. It's a formula for the rate of change. It's a formula for the velocity. All right? Now, what I have written here in red, do you think with a little practice we could go right from that to that? Look at the pattern, okay? This is actually a really good example to see the pattern. I did the power rule on that quantity to get that, and then what did I do at the end? Times the derivative of the quantity. So usually u is a quantity. So it was, and it really is this, isn't it? I take the derivative of the quantity, u, and then I'll multiply the derivative of that quantity times it. See how it works? I know you need to see some more, but any lights coming on? Did you have a question? Okay. All right. Now, as we keep going in the book, at the bottom of page 131, they try to explain it to you another way. So, I'll explain it as many different ways as we can. Something's going to stick eventually. So when applying the chain rule, it is helpful to think of the composite function f of g, that's what this notation means, f of g, as having two parts, an inner part and an outer part. So the derivative of f of u is the derivative of the outer function times the derivative of the inner function. So maybe you like this notation better. There will be times during the year where that notation's better. So y prime equals f prime of u times u prime. F prime of u times the derivative of u. Okay? The derivative of y equals f prime of u times the derivative of u. Do you see that those two things are telling you the same thing, just with different notation? There will be times when that's the notation we need to use because any other type of notation just is too cumbersome to work with. There will be many times when this is the notation we'll use because it's the simplest way to do it. Okay? So, we'll pause here for a second. Any questions? And by the way, this is a theorem. It has been proven to be true. Okay? So don't ask me to prove it because I'd have to just copy something out of the book. All right? But are there any questions on what those two notations are telling you and on why they're the same thing? All right, let's keep working with it then. Now, the general power rule is a version of the chain rule that is extremely helpful. Okay? So we're going to get another notation for the chain rule here. In fact, quite often, when we're actually using the general power rule, we'll just say we're using the chain rule, because this is the most common way of using the chain rule, at least for a while. All right? So, and again, it sounds all complicated here, because it is. If y equals u of x raised to the n, where u is a differentiable function of x and n is a rational number, then dy dx, the derivative of y with respect to x, equals, okay, it's actually easier to look at here, but dy dx equals n, so that's the original exponent, times u of x is our quantity, subtract 1 from the exponent, times the derivative of u. Well, now wait a minute. Isn't that exactly what we did here? If our quantity is u, even if I leave that step out and leave that step out, if I have y equals x cubed plus 1 to the 7th. So what's in the parentheses? That's u of x. According to the general power rule, the derivative of y with respect to x equals, then we did the power rule on this. We did the exponent in front times the coefficient, and then we left u of x alone, then we subtracted 1 from that exponent. That's what all this is. And then what does the general power rule say to do last? Times du dx, times the derivative of u. Isn't that what we did? U is x cubed plus 1, so we did times 3x squared. So the original notation of the chain rule gives us the exact same thing as the notation of the general power rule. So the general power rule is a version of the chain rule. It's a special case of it. Okay? And it's a special case that we use a lot. So the easiest way to memorize the general power rule is like this. The derivative of u to the n equals n times u to the n minus 1 times the derivative of u. Notice, no matter which version, we've had 3 versions of the chain rule now. No matter which version we talk about, the very last thing is the derivative of u, the derivative of u, the derivative of u. It's always the derivative of the outer function times the derivative of u. Okay? Every way we write it, that's the way it works. The derivative of the outer function times the derivative of u. All right, I'll pause here. Any questions? Okay. Let's do another example. So I've got the general power rule written here. Let's find the derivative of y equals 3x plus 2 quantity cubed. According to the general power rule, y prime, or dy dx, however you want to write it, equals exponent of 3 times the coefficient of the quantity, so 3 times 1. Then keep the quantity, keep u, subtract 1 from its exponent, 3 minus 1 is 2, and then times the derivative of u, times the derivative of the quantity 3x plus 2, which in this case is 3. And then there's usually a little bit of simplifying to do with the multiplication. So I'll multiply the 3's together and get that. You follow me? All right. Now what I've got covered up over here is to do it our original way. We would think of that as y equals, question? Mhm. Yep, just a different way of thinking about the chain rule. Does that make sense? Different notation, really. Not necessarily a different way of thinking. I just made it worse, didn't I? All right, so if we've got y equals u cubed, where u is 3x plus 2, if u was just u, and that's all there was, we'd take the derivative and we'd get that. Then we'd multiply the 3's together and get that. Okay? But what is u? It's 3x plus 2. And we get the same thing. So I don't know if I can say the most common mistake. A common mistake, even though I've pointed out that no matter what notation you use, the end of it is always the derivative of u. That's where that 3 right there comes from, right? The derivative of u. A common mistake is people leave off the derivative of u. Okay? And the reason that those of you that are going to do that do is because you're this close to getting it, but you don't quite get it. Okay? So when we're working problems and you realize to yourself, oh, I keep leaving off that derivative of u thing that he warned me about, that means that you're 90% of the way there. But unfortunately, 90% of the way there is not there. Okay? So we'll have to really work on that. Everybody with me? All right. Now, all of our trig functions have a chain rule version because it's not always going to be the sine of x or the cosine of x. It's going to be the sine of x cubed plus 7. Or it's going to be the sine of some horrible looking thing with quotients and products and all, you know, it's just not always going to be x. So the chain rule version, at the risk of repeating myself so often as to become a self-parody, look what's at the end of every one of these. Derivative of u, 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 derivative of u. It's the exact same formula you've already memorized times the derivative of u. Okay? So if nothing else, if you know you're supposed to use the chain rule and you're not sure what all to do something, and then at the end, derivative of u. Okay? And this leads us to this. Let's see, this would be page 136. You need to have all of these things memorized, including the chain rule versions of the trig rules. Okay? All of these are on your cheat sheet that I gave you a few weeks ago. There's a lot of other stuff on there too, but all of this is on there. It may not be the exact same version. I don't remember exactly how I typed them up, but you know, and you're going to have to memorize. You really are. You're just going to have to. But let me warn you, memorizing is not enough. Okay? Memorizing the formula and being able to successfully use it are two different things. Now, granted, you can't successfully use it if you don't know it, but just knowing it's not enough. So it's memorize and apply. So memorize it, and then we're going to do a bunch of problems for you to apply it. But don't forget to memorize it as you're going. And memorize however you memorize. If you're the kind that needs to just sit there and stare at it for 30 minutes, then sit there and stare at it for 30 minutes. If you memorize better, just, you know, memorizing things as you use them, then do it that way. I don't care what method you use. I'm just telling you, though, the faster you have this stuff committed to memory, the easier the problems are going to be because you'll know what to do. You know, when you see, oh, I need to take the derivative of cotangent, you won't be like, I don't know what that is. Well, if you know what that is, when you're faced with, oh, I need to take the derivative of cotangent, then it's not a problem, is it? Okay? All right. Let's do some examples. So I'm on page 137. In exercises 1 through 6, they do not say take a derivative. They say complete the table. So these first few problems are simply an exercise in seeing what, or understanding the notation and understanding what's U and what's not. So for number 2, they give us that y equals 1 over the square root of x plus 1. And then the next column over, we're supposed to fill in u equals g of x. So in other words, we have to say what u equals. Now, there are a few things, and as we go through the year, we will revise our guidelines just a bit, but you're looking for a quantity with an exponent on it, okay? So if you look at 1 over the square root of x plus 1, the only quantity I see is x plus 1. And it does have an exponent on it because square roots are exponents of 1/2. And an exponent of 1/2 in the denominator is the same thing as an exponent of negative 1/2, right? So u equals x plus 1. Then the next column and our last column, they want us to write that as y equals f of u. So in other words, replace the x plus 1 with a u. So I'd get y equals 1 over the square root of u. Now, and we're done. We've done all the book asked us to do. The only thing I'd like to add to that, because they don't tell us take the derivative. We don't have to do the derivative. Is that's not written in the form I'd want to take the derivative of, is it? So I'll go ahead and change that to u to the negative 1/2. Now I can take the derivative of it. I don't have to. The directions don't tell me to. But I have it ready now to take the derivative of it. Okay? Let's try number 4. All right, y equals 3 times the tangent of pi x squared. I don't see any quantities with exponents on it. But one of the other things I need to look at is whenever I have trig functions involved, quite often the angle part, the theta part, is the u. It's not always, but quite often it is. Just like we can't always say it's a quantity with an exponent on it, we can't say that it's always the theta part of a trig function, but quite often it is. So what's the theta part of this trig function? Pi x squared. So let u equal pi x squared. And then all we have to do for the last step is to rewrite that with u instead of pi x squared. So y equals 3 times the tangent of u. We haven't done any derivatives. All right, do number 6. See what you come up with. Did you get what I got? All right, there are 13 examples in this section in the book. I would not ignore those if I were you. Okay? Now, I don't know if I'd worry about them today, but at some point you need to go back through and make sure that all of those examples make sense to you. And the way I would do it is I would read the question, I would cover up what the book did, I'd try to work it myself, and then see if I got the same result. Okay? I wouldn't do that yet, but I'm just pointing out before we're done, before we have the quiz, you need to do that. Okay? Let's do number 12. Now, on number 12, we have g of x equals the square root of 5 minus 3x, and we're supposed to find the derivative of the function. First thing I'm going to do is rewrite that square root as an exponent of 1/2, and when I do that, I start thinking general power rule, okay, because I have a quantity with an exponent on it. So this is definitely a chain rule problem, and I think the best version is the general power rule, which says this: the derivative with respect to x of u to the n equals n times u to the n minus 1 times the derivative of u. That's the version of the chain rule I'm going to use this time because it seems to be, well, this problem seems tailor-made for it, to be honest with you. Okay? So, g prime of x equals, then we apply the general power rule, which is the chain rule. So, exponent times coefficient. So, 1/2 times 1 is 1/2. U, 5 minus 3x, subtract 1 from the original exponent, 1/2 minus 1 is negative 1/2, times the derivative of u. Now, we never wrote out u equals 5 minus 3x, but doesn't u equal 5 minus 3x? So the derivative of 5 minus 3x is negative 3. So as we've done so often, we had the one step of calculus, and now we just try to simplify our answer. So, and I'm going to try to do this in one step. See if you can follow me. When I multiply those factors out, I have one of them negative, so I get a negative, don't I? Then that 3 will be in the numerator. The 1/2, isn't that the same thing as a 2 in the denominator? And then a quantity that has an exponent of negative 1/2. I can put that in the denominator, make it an exponent of positive 1/2, and even better than putting an exponent of positive 1/2, square root. So I could do all that in one step. Okay? Now, just let me point out, because I don't want you to forget the original notation. That is the dy dw, is the dy du from the original chain rule notation. And amazingly enough, the du dx is the du dx from the original notation. I know. Nobody saw that coming. Okay? Do you see why what I circled in red, the n times u to the n minus 1 is the dy du? If I just gave you u to the 1/2 and said take the derivative of it, wouldn't you do that? Isn't that what I have circled? Okay. Let's take a look at number 20. All right, we're still just finding the derivative. For number 20, we've got y equals negative 5 divided by t plus 3 quantity cubed. Now, I can quotient rule this, and when I do the derivative of the bottom with the quotient rule, I'll have to use the chain rule on the t plus 3 quantity cubed, won't I? Okay? So I can do that. I'm not going to, but I can do that, and you can too. What I'm going to do is I'm going to take advantage of the way exponents work. A quantity with an exponent of positive 3 in the denominator is the same thing as that quantity to a negative 3 exponent in the numerator. Now, I can just use the general power rule now. I don't have to use the quotient rule and then the chain rule inside of the quotient rule. I can do that, and we'll work somewhere we do that, okay? But right now, I think this is simpler. I only have to apply one rule instead of two rules, okay? So, y prime equals. All right, the general power rule says exponent times coefficient. So negative 5 times negative 3. I actually wrote it as coefficient times exponent, but you get it. Exponent times coefficient. U, our quantity, t plus 3, subtract 1 from the exponent. Negative 3 minus 1 is not negative 2. Negative 3 minus 1 is negative 4, times derivative of u. What's the derivative of t plus 3? 1. And I think I can simplify this all in one step. Negative 5 times negative 3 times 1 is a positive 15. Then instead of a quantity with a negative exponent, how about put that quantity in the denominator, make the exponent positive. All right? Just so that we're not forgetting the original chain rule notation. That's the dy du. That's the du dx. Or du dt in this case, since it's t. Okay? Because if I gave you negative 5 u to the negative 3, said find the derivative, wouldn't you get 15 u to the negative 4? So that's the dy du. Then if I said, oh yeah, times the derivative of u, which is 1, we used the chain rule. We're calling it the general power rule, but the general power rule is just a version of the chain rule. Have I said that enough? I haven't. You think I have? I haven't. Not my first rodeo. Number 26. We're still finding the derivative. So I've got y equals 1/2 x squared times the square root of 16 minus x squared. This is a product rule problem. There's no way around it. This is a product rule. That's the first function. That's the second function. So we've got to product rule this. Okay? So the product rule says the derivative of a product is the first function, 1/2 x squared, times the derivative of the second function. Now, to take the derivative of the square root of 16 minus x squared, we have to use our brand new chain rule. And in fact, I'm going to think of this as the general power rule. That square root of 16 minus x squared, mentally, put a parentheses around the 16 minus x squared and an exponent of 1/2 on it. Okay? So to take the derivative of that, I do the general power rule. So exponent times coefficient, exponent of 1/2 times the coefficient of 1. U, which has got to be the quantity, right? It's got to be the 16 minus x squared. So 1/2 u to the n minus 1. So the original exponent of 1/2 minus 1 makes that a negative 1/2 times the derivative of u. So times, well, the derivative of 16 is 0. The derivative of negative x squared is negative 2x. This opens lots of doors, doesn't it? There's lots of things we can do now. Oh, by the way, that's just the first half of the product rule. That was the first function times the derivative of the second. Everybody with me? Plus the second function, which I could write as the square root of 16 minus x squared, but since I've gone to exponential notation, I might as well go to exponential notation. 16 minus x squared to the 1/2 times the derivative of the first function. So the derivative of 1/2 x squared, use the combination rule on it, exponent times coefficient, 2 times 1/2 is 1, x, subtract 1 from the exponent, 2 minus 1 is 1, so I get x. All right, that's our step of calculus. The next 4 steps or so are all going to be algebra. You with me? All right. All right. A very, very common technique, you might as well learn to love it, is to factor when we get to this step. Okay? So let's see. Let's look in front. Everything's based on in front of the plus sign, behind the plus sign. So I see an x as a factor, and I see, you know what I need to do before I factor out? I need to simplify. So hang on. Let's simplify. It's still all based on this. Let's simplify in front of the plus sign. We'll simplify behind the plus sign. In front of the plus sign, let's see. I have a 1/2 times a 1/2 times a -2. What is 1/2 times 1/2 times -2? -1/2. So I took care of that, and that, and that. Then I see x squared times x. X squared times x. So I've used that, I've used that. And by the way, don't actually mark that out like that on your paper. If it helps you to underline it or put a light slash, okay, but you might make a mistake and have to erase your marking it. So don't obliterate your work like I've done. All right, then I've got this quantity to the -1/2. Behind the plus sign, I don't have much. I have an x, and I have that same quantity, this time to a +1/2. So I've simplified in front of the plus, simplified behind the plus. Now I'm ready to factor. So now, let's see what I've got here. Let's not worry about the constant for a moment. Let's look at x cubed and x. What's common to x cubed and x? The x cubed, the x. So I factor out the x, like so. Okay? Then I see this quantity both places. So I have a common factor of 16 minus x squared. The question is, which exponent do I use when I factor it out? The big one or the little one? The little one. Always use the smallest exponent. So I factor out a 16 minus x squared to the -1/2. And then you may be wondering, what did he scribble out in front of the x? This is one of those where sometimes it's beneficial, sometimes it's not. You might think, well, okay, I see the -1/2 as a factor in front of the plus sign. I don't see one here behind the plus sign. You are correct. You don't see one there. But I'm factoring it out anyway. You'll see. You'll see. Okay? So my greatest common factor is -1/2 x 16 minus x squared to the -1/2. So that is my greatest common factor. All right? Let's see what we're left with when we divide this out. So again, in front of the plus sign, Well, if I divide negative 1/2 by negative 1/2, I get a coefficient of 1, right? Negative 1/2 divided by itself is 1. X cubed divided by x is x squared. And then that quantity with the negative 1/2 divided by that exact same quantity to the negative 1/2 is another factor of 1. So I've got 1x squared times 1, which is just x squared, right? With me? I know you don't know why I took out the negative 1/2, but do you see that once I decided to, when I divide what's in front of the plus sign by negative 1/2, that's a 1. Divide by x, that becomes, or divide by x, that becomes an x squared. Divide that quantity by itself, I get another factor of 1. So all I get is x squared. Factors of 1 I don't have to write down. All right, behind the plus sign. Well, let's see. All right, I've done it now. I've divided out that negative 1/2 from nothing. Oh, really? From nothing? From 1. What's 1 divided by negative 1/2? It's negative 2. It wasn't a silly thing to do after all, was it? Okay. And then what's that quantity to the positive 1/2 divided by the same quantity to the negative 1/2? When you divide factors with the same base, subtract the exponents. So 1/2 minus negative 1/2 gives us an exponent of 1. So I get 16 minus x squared. Yeah, there's a little scary. All right, now, let's start simplifying. Well, start simplifying. Let's keep simplifying. All right, what am I going to do with that negative 1/2? Negative I can stick out in front. What should I do with the 1/2? Put the 1 where and the 2 where? 1 will go in the numerator, 2 will go in the denominator. I'm not actually going to write down a factor of 1, because unless that's the only thing I have, I don't need to write down the 1, right? So I'll put the negative out in front. I'll put the 2 in the bottom. So I've taken care of the negative 1/2. So where's the x go, top or bottom? Top. A quantity to the negative 1/2. Where should I put that? Bottom. Make the exponent positive. So I did that. And then look at the bracket. The bracket's got to go in the numerator, doesn't it? Well, let's start simplifying it. So I've got the x squared, and then negative, distribute the negative 2. Negative 2 times 16 is negative 32. Negative 2 times negative x squared is positive 2x squared. All I need to do now in the numerator is combine like terms inside the parentheses. X squared plus 2x squared is 3x squared. So I've still got the negative out in front. I've got x times the quantity, 3x squared minus 32. And the only thing I need to do in the denominator, instead of that exponent of 1/2, let's make it a square root. You may want to look at that one again before long.
Yeah.
All right. Your assignment. I feel like Mission Impossible, but I don't want to say if you choose to accept it, because that's giving you an option and you have no option. Your assignment that may or may not end in your destruction. Page 137, 1 through 32, 41 through 46. We did not get as many examples done as I wanted. Most of these you have an example of that's similar. Some you don't. Get as many of these done as you can get done.